So we're going to go over PWM here real quick. This is kind of specific to fan controllers, but it is how PWM works. I covered in a previous video talking about the AutoCool controller from AutoCool Guy and the cycle rate, the pulse rate of his controller versus the Flex-a-Lite controller, which I have here on the bench. I switched out my Flex-a-Lite controllers for the AutoCool Guy controller because the switching rate of the Flex-a-Lite controller is actually much too slow. And actually that's the purpose of this video, is to show that, and it's exactly as I suspected. It's about 44 hertz. That's pretty slow. So the pulses are not fast enough, which causes the motor to kind of vibrate. Mechanically, it makes a bunch of noise because the pulses are too slow, so the motor actually has time to stop in between pulses. Well, it doesn't actually stop moving, but it slows it down significantly, which is why it would shudder. In my case, the Spall fans failed from that. It caused arcing in the brushes and some significant damage to the brushes and to the commutator. I've actually got a video coming on that. But anyways, so I just wanted to show you guys what the PWM looks like coming out of this thing. You guys are just going to say, well, this is just a squiggly line here. Well, yeah, it is, but it's there's more to it. There's more in here than you think. So what is on the screen here is the PWM output from the controller. I have it rigged up to a battery right now. I've got a resistor in the circuit that makes it think that the temperature sensor is in there. So I'll use that just as a test because I don't have anything to actually use the sensor right now, but this is fine. We've got this resistor hooked up right here. And if you're familiar with the Flex-a-Lite controllers, this is kind of specifically about them, but in general, this would be good information for PWM to understand what's going on. This controller has the sensor, and then there's a pot on the unit that is adjustable, and that pot sets the set point of what temperature you want it to come on. These controllers, and I suspect it's probably because the switching rate is so low on it, they start at 60% speed and go up from there. It's sitting right about 60% right now would be my guess, just by looking at it, because what we're looking at here is this is the 12 volt. This is 12 volts right here. Okay, you'll notice that the RMS, the root mean square reading right here, is actually at about 11 volts. It's because I have it dialed down. My nominal is about 12.4 coming out of the test battery I've got right now. So the perceived voltage, because we're pulsing the 12 volts off every so often. The entire cycle of the on off to on is about 22 milliseconds or 44 hertz. So what we're doing is we're removing power every so often, and it happens rapidly. You wouldn't be able to see it without a scope, obviously, but we're pulsing it off every so often. I think I'm at 5 volts per division, or 5 milliseconds per division right now. So about every 7 milliseconds we have a cycle off to on. Let's double check this here. Let's see. Yeah, we were at about 5. Yeah, we're at about 5 milliseconds per division, which is each division on the grid here. So about every 7 milliseconds it turns off and back on. As I increase and decrease the temperature, it's going to change that. So as I increase the temperature, well, now I've gone too far and it's actually going to turn off because I've changed the temperature enough where it's below that 60% threshold. It doesn't go below 60%. So I'm going to turn the temperature back down a little bit, get it to turn on. So let's see here. That right about here is about the minimum. So this is if you look at this is about 60% of the time right here. So it's a little bit more than half. So I'm modulating it off for a period of time. If I rotate this further down to look for even lower temperature, you're going to see it's going to increase even more. So my off time is less and less and less as it gets hotter and hotter. So that's how this system works. It as the temperature rises with the fans on, it's going to continually give it more on time, less off time. Okay, until eventually I'm going to get to a place where, as the temperature keeps increasing, I'm kind of simulating that by turning the temperature pot. This becomes smaller and smaller and smaller, and the less change that there is, the less noise you're going to have in the output. So when I say noise, I'm talking about electrical noise, because this is effectively almost kind of like AC right here. So, we're on like 90% right here and off like 10%. And then eventually with this particular controller, if it gets hot enough, if I turn this down, now it's just a solid 12 volts. So you see I'm at about 12.4 volts here. So let's take a look at that voltage again. As I lower the temperature, it's going to start PWMing. So let's see if we can't. There we go. All right. So you're going to notice as it PWMs, the voltage is dropping because the perceived voltage. This is a little difficult to do here with one hand. You're going to see the perceived voltage. See, is about 11.3. So the change in voltage is actually not that big, but it's enough, and it'll be more when the voltage is higher, when the voltage is up around 13.5 volts. I've got this battery hooked up that's a little bit low. It's like at 12.4, 12.3. So you'll see I'm at about 10.8 right there. Let's see. There we go. Yeah, right about there. So anyways, you can see what happens. The on time decreases as the speed goes down. The off time increases. As the temperature goes up, the on time increases and the off time decreases. And it's happening. It's pulsing this. So let's say I had it at about 60% right now. It's doing this every 40, it says 43.9. It's about, I think it's supposed to be about a 44 hertz signal. So it's doing it 44 times a second, right? It's doing one of these cycles here, on to off to on. It's doing that 44 times a second. If I do that a lot more frequently, you're still 60% of the time, and you're still off 60% of the, off 40% of the time. Stumbling over my words here. So 60% on, 40% off, right? If you do that 10 times faster, you're still 60-40. So 60-40, 60-40, but you're doing it a lot faster. The faster you do that, the better your signal is going to be, because it's a lot smoother. The off those pulses are a lot more frequent, allowing a much smoother DC signal to your motor. Particularly with the Spall fans, and I think it's because they're high torque fans. They're very high torque motors, and they're more responsive to voltage change. If you're doing it too slow, the vibration mechanically just destroys those motors. I learned that the hard way. I ruined one that way. So the AutoCool controller, it's doing this pulsing at 7,000 times a second instead of 44 times a second. So obviously there's a massive difference there. So I just wanted to kind of go over what's going on here. And this is the case with PWM in general. This is what's happening. You have some amount of time that's on and some amount of time that's off. If you want half speed, it's going to be 50 on, 50 off. You want full speed, it's going to be 100% on, and it'll never be off. You want 30% speed, it's going to be on 30% of the time, and it's going to be off 70% of the time. Anyways, that is how PWM works. It's really not all that complicated. When you can get a scope and actually look at what's going on, it makes a whole lot more sense. So this again is kind of an analysis of the PWM controller from Flex-a-Lite. Good controllers. I've used them on my Flex-a-Lite fans on other vehicles that I have. They're quality units. I've never had one fail, but they're not real high tech as far as PWM goes. It's a very slow PWM, which makes it very noisy. If you run it at 100% all the time, it's probably not that big of a deal because you're just seeing the PWM as it ramps up the speed. I'll give you an example of that. As I dial this down here, you'll see, or excuse me, dial it up. It's going to turn off. So there, it's going to turn all the way off. If you were to full on this thing, you're not going to get a whole lot of time. So here, let me full on it. You'll see what happens. So you don't get a whole lot of time where it's PWMing because it's just going to go all the way up to full speed here. So, that probably won't cause any damage to a fan motor, but if you want to actually run it using the temp sensor where it's going to vary the speed based on temperature, that will destroy some fans. So you have to watch out for that, specifically the high performance ball fans. The higher the torque the motor, the more sensitive it's going to be. So I've rambled long enough. I'm hoping that this is helpful. I know there's a lot of folks that don't understand PWM, but I think the visual helps a little bit. So anyways, that's about PWM and the Flex-a-Lite controller.